Welcome back. So next we want to look at the principle of mathematical induction. Uh, when we're talking about mathematical induction, this is a way of proving some mathematical statements which are valid at every counting number or at every natural number. You now know what natural numbers are. So it's very important properties of positive integers or natural numbers. And it is used for proving statements involving all positive integers. So when we are trying to find a way of proving something that it is valid or it is true when n is equal to 1, 2, 3, 4, these are counting numbers, you can make use of the mathematical induction. So when you're doing the mathematical induction, proof by induction, this is the usual mathematical induction that you know from your A-level mathematics. When you're doing proof by mathematical induction, this is what you're doing. You want, these are the steps that you're supposed to follow. And the steps follows a logic that if you want to prove that something is true for n equal to 1, 2, 3, 4, 5, if you are able to assume that it is true for n equal to 1, and if we let k be any number, any positive integer, and if we are able to show that the statement is true for k equal to 1, for n equal to k, sorry, if we're able to show that the statement is true for n equal to k, then if you are then able to show that the statement or whatever mathematical statement that you want to prove, that it is also true for n equal to k plus 1, where k is an integer, then since k can take any number, n equal to 1, 2, 3, 4, 5, and if it's true for n equal to k, and if it's true for n equal to k plus 1, then it means by logic it is true for any counting number, n equal to any counting number. Because it is true for n equal to k, then we have also proved that is true for n equal to k plus 1, where k is any counting number. Therefore, we would have shown that the statement is true for n equal to 1, 2, 3, 4, 5, going upwards. So these are the steps that you follow. First of all, you have to prove that the statement is true for n equal to 1. Or sometimes the statement might not start at n equal to 1. It might start at another positive integer, which is the smallest one. That's the initial step. Sometimes you see some statements that you're going to prove, they may start at n equal to 5, n equal to 10, n equal to 6, whatever. So in that case, you are not necessarily proving that it is true for n equal to 1. You have to show that the statement is true for n equal to the first smallest positive counting number. Okay, that's the first step. Then the second step is to make an assumption. Here you are not proving anything. Assume the statement is true for n equal to k. Just let your n be equal to k and assume that it is true. So generally, the second step, you are just substituting in your formula where there is n, you are just putting k, and that's an assumption. Then the important part of the proof is step number 3, whereby you are using your assumption in step 2, from the assumption in step 2, to prove that the statement is also true for n equal to k plus 1. If you are able to show that from your assumption in step 2, if you are able to show that the statement is true for n equal to k plus 1, then you have done the proof. Then you make a final conclusion, which is step number 4. Since the statement is true for n equal to 1, then it must be true for, it must then from step number 3 there, because we've shown that it is true for n equal to 1. Then from step number 3, it should be true for n equal to 2, n equal to 3, n equal to 4, because we have shown that step number 3, we have shown that it is true for n for k plus 1. So if it's true for k equal to 1, it should be true for n equal to 2, n equal to 3, n equal to 4, and so on. Why? Because 1 plus 1 is equal to 2. So if we have shown that it is true for k plus 1, then we have shown that, and if it's true for n equal to 1, then it is true for n equal to 2, n equal to 3, and so on. Then the statement should be true for all other positive integers. That's your conclusion. Like for example, the example is for any positive integer n, can you prove that 1 plus 2 plus 3 plus 4 up to a certain number n is equal to n, open bracket, n plus 1 over 2? Okay, so here n is whatever positive number that we are last adding, the last term of our summation of counting numbers. So if I want to prove that it is true for n equal to 1, it means I am adding all counting numbers up to 1. So it means I'm just adding 1, in other words. Because the statement that you want to prove here is the sum of counting numbers up to 1. The sum of counting numbers up to 1. So it's the sum of counting numbers up to n. Then that n, if I put it n and say n plus 1 over 2, I get that sum. Okay, so it's the sum of counting numbers up to a certain number n. So if my n is 1, it means I'm just saying 1. Okay, then that should be equal to, if I go to that formula here, n plus 1 over 2, and put 1 here, that should be equal to 1 plus 1 plus 1, which is 2. 2 times 1, that's 2. 2 over 2, which is 1, which is true. So 1 is equal to 2 over 2, which is 1. So this is clearly true for n equal to 1. Then the next step is to assume that this statement is true for n equal to k. So in this step, we are just substituting where there is n, we are putting k. So which means we are saying 1, 2, 3, 1 plus 2 plus 3 plus 4 up to k should be equal to k plus 1 over 2. Then the task now is to prove that it is true for n equal to k plus 1. So if it's true for n equal to k plus 1, when n is equal to k plus 1, it means I am adding counting numbers from up to k, then plus k plus 1, because k plus 1 is the other term which I'm adding, which is the next term after k. So if I am proving that this statement is true for when n is equal to k plus 1, it means I am adding all counting numbers up to k plus 1. Since I have added previously all counting numbers from k and have shown that I assume that it is equal to this, then I just add k plus 1 from this, because this is a sum of natural numbers. So if I add k plus 1, it means now I'm taking this assumption right hand side and also add k plus 1. And I want to show that this is equal to k plus 1 plus k plus 2 over 2. So by just simplifying these simple terms, which is a fraction over 1 there, we combine these fractions, that's the proof. And then our common denominator is 2 into 2, 1 times this denominator times this numerator, which is k plus 1 plus the denominator here is 1 times 2, which is 2 times k plus. So we're just adding these fractions. Then if I simplify this numerator by expanding the bracket, I get k squared plus 3k plus 2. Then factorize this, I get k plus 1 times k plus 2. That's the factors. But what I want to prove is, I want to prove this statement when k is equal to k plus 1. So you can clearly see that this is k plus 1, and this is k plus 1 plus 1. So where there is k in this statement, there is k plus 1 in this proof, which is true. So if I'm able to deduce that this sum is equal to k plus 1 plus k plus 1 plus 1, because this is k plus 1. Where there is k, I'm putting k plus 1. So this is k plus 1, k plus 1 plus 1, which is k plus 2. Then it is true for this. This shows that this statement holds for k plus 1, which means that the statement, hence this statement is true for 1. So when you're concluding this, how you conclude? By induction, it is true that the statement is true for when n is equal to 1. By induction, it's true that this statement is true for n equal to 1, n equal to 2, n equal to 3, and n equal to k, and n equal to k plus 1. Therefore, it is true for any natural number. Another example is to prove that for any natural number. 1 plus 3 plus 5. So you can see here we are adding even numbers. Okay. Plus 2n minus 1 is equals to n squared. Okay. 2n minus 1 is equals to n squared. Like the proof that I just explained above, we have to show that it is true for n equal to 1. So when n equal to 1, the left hand side becomes 1. Okay. Because if I put 1 there, I'll get 2 minus 1, which is 1 up to 1. So 1, which is equal to 1 squared, which is also equal to 1. So it is true for n equal to 1. Then I assume that the statement holds for n equal to k, which is this statement, the same statement, but just substituting k, n by k. Then the task now is to prove that it is true for k plus 1, for n equal to k plus 1. Now, when it's true for n equal to k plus 1, it means I'm adding all the not the even number, the odd numbers. 1 plus 3 plus 5 plus 7 plus 9 plus what? Plus, remember previously I've added all the even numbers up to 2k minus 1. So what is the next even number when n is equal to k plus 1? So the previous even number that I've added is 2k minus 1, which is this one. Then the next even number becomes 2k plus 1 minus 1. Okay, so this is the term which I am adding. Okay, this is what I'm adding from my assumption above. So if I added this term which I've just highlighted here from above, it means if I also add this highlighted term here where there is k squared, and I'm able to get my formula, which is k plus 1 squared, then the proof is done. So I'm going to add this term, this n plus 1th term here where there is k squared. So it becomes k squared. If I simplify this becomes 2k plus 2 minus 1, which is 2k plus 1. So this is what I have. And then if I factorize this thing, I get k plus 1 squared, which is true because when n is equal to k plus 1, it means I am proving when there is n here, I'm just putting k plus 1 squared, which is true, which shows that it is true for k plus 1. Therefore, it is true for n equal to k plus 1. Therefore, by induction, it is true for n equal to 1, n equal to 2. Therefore, it is true for n equal to 1, n equal to k, n equal to k plus 1. So it shows that it is true for any natural number. So I've proved that by induction. Similarly, you can also, maybe I'll explain this one a bit. This is no longer an equal statement, but it's an inequality. Can you prove that 3 to the power n is always greater than 2 to the power n for all natural numbers n? So we want to prove this statement for all natural numbers. Similarly, like our method, we show that this statement is true when n equal to 1, but this is a greater than sign. It's no longer an equal sign like the previous proofs. So you need to be very careful there. Okay. So when n is equal to 1, we're just showing that 3 to the power 1, which is equal to 3, is greater than 2 to the power 1, which is equal to. So which is true. 3 is greater than 2. Okay. Then we assume that the statement is true when n equal to k, which is 3 to the power k is greater than 2 to the power k. Okay. Now the task now here we want to apply logic. You need to listen. Remember previously we were looking at inequalities. That's what we did previously. We now know the properties of inequalities. So we can apply that to prove that when we assume that this is true, then can we also prove that when n is equal to k plus 1? So generally what we want to do is to prove that 3 to the power k plus 1 is greater than 2 to the power k plus 1. But first of all, we know that 3 to the power k plus 1, by laws of indices, it means that if you are adding the powers, and then you should be multiplying the base. Okay, so 3 to the power k plus 1 is similar to 3 to the power k times 3. Okay, are we together? And then 2 to the power k, and then we want to show that we want to prove that this is true here. Okay, But we know that from this hypothesis, this assumption that we have shown here, so we know that, okay, this statement that I just explained, that I just expanded, which is 3 to the power k plus 1, which is equal to that. We know that this is greater than 2 to the power k times 3. Why is it, are we saying this is greater than this? By applying our inequalities, we know that if we are multiplying this one by 3 by 3, there's 3 both sides. Are we together? Then we have got 2 here, and you have got 3 here. So automatically, since these are natural numbers, automatically this should be greater than this. Okay. We want to link it with the 2 to the power. We want to link it with the 2 to the power k plus 1. Okay. Right. Then we know that by applying our inequalities, the laws of real numbers that we discussed previously, we know that this thing should be greater than 2 to the power k times 1. Because this number, this one I'm multiplying by 3, this one I'm multiplying by 2. And 3 is bigger than 2. Therefore, this should be bigger than this. Because 2 to the power k is the same as 2 to the power k. The difference is here I'm multiplying by 3, here I'm multiplying by 2. So automatically, this one which is being multiplied by 3 should be bigger than this one which is multiplying by 2. So this is bigger than this one. And this one is known to be, since, and then there's the explanation, since 3 is bigger than 2. So this one, because 3 is bigger than 2, it automatically means that 3, this statement is bigger than this statement. Then this statement is equivalent to the left-hand side of the hypothesis that you want to prove, which is 2 to the power k plus 1. Because if I apply my laws of indices here, 2 to the power k times 2, I'll get 2 to the power 3k, k plus 1. So automatically it means this whole thing, by using the transitivity law of real numbers, it means if this one is bigger than this, and this one is bigger than this, therefore this is bigger than this. Okay, you remember we said if A is greater than B, then B is greater than C, then automatically A is greater than C. Okay, so this thing here is bigger than this, and this one is bigger than this, which means this is bigger than this. Okay, so which is true. We have shown that it is true. We are using logic here. You need to be able to follow that. Therefore, by induction, it shows that 3 to the power n is always greater than 2 to the power n for all natural numbers. Since it is true for n equal to 1, n equal to k, and n equal to k plus 1, therefore it is true for all natural numbers. Then you should also be able to prove that for any integer, that's another example, for any integer n which is greater than or equal to 1, then 2 to the power n plus 1 minus 1 is divisible by 3. If you want to prove that if a number is divisible by 3, then it should have a factor 3 somewhere there. Let's see if we are able to prove that. We may want to prove that it is true for n equal to 1. So we just put where there is n here, put 1. Which is, if I put 1 there, that's 2 times 1, which is 2 to the power 2 minus 1, which is 4 minus 1, that's 3. And since 3 is divisible by 3, hence it is true for n equal to 1. Then we assume that this is true for n equal to k, which means if we assume that it is true for n equal to k, we are just assuming that, what it means to assume that this statement is divisible by 3 when n is equal to k. When this statement is divisible by 3, it means there is an integer L that you multiply 3 with to get this statement. In other words, we are saying if this is divisible by 3, if 2 to the power 2k minus 1 is divisible by 3, it means there is an integer L that you multiply 3 with to get this statement. So in other words, we are saying 2 to the power 2k minus 1 is equal to 3L, where L is an element of integers. Okay, because it is divisible. A number which is divisible by 3, it means there is a number, an integer that you multiply 3 with to get that. And otherwise, 3 gets into that number. If 15 is divisible by 3, then it means there is an integer. That means 3 can get into 15, a whole number, into 15 full whole numbers, or there's an integer that you multiply 3 with to get 15, which is 5. So in other words, if we are saying this is divisible by 3, it means there's an integer L that you multiply with 3 so that this is equal to this. Okay. Then the next thing now is to prove that now for n equal to k plus 1, which means we want to prove that 2 to the power 2k plus 1, where there is n minus 1, is divisible by 3. Okay, which means we want to show that there is an integer that we multiply 3 with to get this thing. Otherwise, if you are able to factor out 3 somewhere there, then you have proved that it is divisible by 3. Okay, so this thing here is equal to, if I simplify these indices, because I want to link this with my assumption here. Okay, so that I'm able to substitute my assumption here somewhere here. Okay, so what do we have here? This is equal to, if I simplify these powers, you see that this is equal to 2 to the power 2. I want to separate these powers into 2. Okay, so this is equal to, since I'm saying 2 to the power is 2k plus 1, it means it is equal to 2 to the power 2 and 2 to the power k plus 1. Okay, or I can just multiply by k there, by k there. Okay, I can multiply by 2, sorry, by 2k times 2. Okay, that's okay. I multiply by 2 there, 2k plus 2, which means I am saying, or if I'm multiplying the powers, you know the laws of indices. If I'm multiplying by the powers, it means I'm saying 2 to the power 2 times 2 to the power k plus 1. Okay, so what does that mean now? Times k plus 1, it means I'm saying what? I'm saying plus 2 to the power 2. Okay, so this simplifies to 4, because 2 to the power 2 is 4, times 2 to the power k minus 1. Are we together there? 2, that's 2 there, that's 2 there. Okay, so that's 4 2 to the power k times minus 1. But we know that from this assumption here, we know that 2 to the power k is equal to, if I move 1 going there, is equal to 3l plus 1. Okay, so it means where there is 2 to the power k, I can put 3l plus 1, which is 3l plus 1 minus 1. Okay, then I simplify this becomes 12l plus 4 minus 1, which is 12l plus 3. Then since there is 3 there. Remember, this is equal to our left-hand side, this whole thing. Since 3 can get into 12, 3 can get into 3, it means I can factor out 3 there. And then if I factor out 3, I'm left with 4l plus 1. Since I'm able to factor out 3, it means this thing is divisible by 3. Because if I divide by 3, 3 and 3 will cancel. And remember, L is an integer. So it means this thing is divisible by 3. Because I'm able to factor out 3 from this thing. So it is true. Then by induction, it shows that 2 to the power 2n minus 1 is divisible by 3 for any being an element of integers. Then next, there's a tutorial. Tutorials are for you. So you have to make use of these tutorials to help you to practice. I am available if you face any challenges through these tutorials. So you go through all these questions. They include the number system, proof by induction. And this tutorial, this is where I usually source my examinations and my assignments, my tests. So please go through that tutorial and try to get into group discussion with the other friends. Then when you get into those group discussions, if you face any challenges, I'm available to help you. So this marks the end of chapter 1. The next lecture, we are going to look at sequences. Okay, the next lecture, we are going to look at sequences. So for now, we can end this lecture here.